All right, welcome to Math372, Lecture 8, Complex Analysis. This is the continuation of the glory of Cauchy. So we're going to see how to integrate without integrating. All right, so the reason we can do this is we've spent the time proving this great result, Cauchy's formula, and we can get consequences of it. What we've been doing is if that was an oh God, yes, that's exactly what you should feel here. It is so beautiful. You should be screaming out to the Almighty, for gracing us with such a formula. So we've paid the burden, we've paid the piper to prove this result. We've been essentially using the following formula and almost deriving it from scratch every single time we need it. So what I want to do now is I want to just state a more useful thing. So theorem, Cauchy's residue theorem. And we're only a few lectures away from Riemann making an appearance. So let F be holomorphic in open omega except at finitely many points. Let gamma be a simple closed curve in omega whose interior is in omega. Let z1 to zn be the points inside omega where F has a finite pole. F has no poles on omega. Then the integral over gamma, 1 over 2 pi I, f of z dz is going to be the sum. What should I not use for my index of summation? I, okay? Never, ever use I as an index of summation in complex analysis. K goes from 1 to n of the residue of f at zk, where f of z is going to be a sum. M goes from minus n of k to infinity. I'll do it as maybe akm z minus zk to the m. So I'm doing some kind of Taylor series expansion about the point zk, and so I just wanted to note that these coefficients can be different at different places. And the residue of f at zk is going to be the -1 term in the Taylor series expansion. So essentially all that matters when you integrate is the -1 term in the Taylor series expansion. We have essentially already proved this. What we've done is implicit from before. Right? We just basically reproved it every single time. I would give you some closed curve gamma. So here's our curve gamma. Here would be the points, z1, z2, zn. Here are the points where the function would blow up. And then what we would do is we would come along, do our little circles, and come back. Right? And we would say that f is now holomorphic, and then we'd have this big closed curve gamma. We'd have a slight thickness in all of these, a slight separation. And then by Cauchy's theorem, that would all be 0. Then we would take the limit as the gap goes to 0, and those would all cancel. And then each of these circles would be of radius epsilon, and all that would matter would be the 1 over term in the expansions there. So we already have this theorem. But we kept proving it again and again and again every single time we needed it by drawing this picture. So the whole point is, let's stop drawing this picture and let's stop going through this. Let's just isolate this as a theorem and use it. Now, the only thing that you have to be careful about is, what are your conditions? We are not proving the Jordan plane curve theorem, although there's a non-zero chance that someone in the class might do that and might present to the class on it. We will always assume we have curves where we have a clear interior and exterior. Also note that we do not want to have a pole on the line of integration. You don't want to go through an infinity. If you have a pole on the line of integration, what should you do? Yes?
You should integrate around it.
You should integrate around. You should detour. You should either go up or go down and then take some kind of limit. And then you'll have either, if you go down, so it's above you, you might now entirely include that pole in what you're doing. And if you do the other direction, you won't include it at all. But you'll still have like it going in, half of it going in the other direction. So there's some language in here that's implicit that I think you've known, but I will just go before. We say f has a 0 at zk of order n greater than or equal to 1 if we can write f of z is an z minus zk to the n plus an plus 1 z minus zk to the n plus 1 plus dot 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 dot. So for example, f of z equals 1701 z cubed plus 1997 z to the 8th has a 0 of degree 3 at z equals 0. Okay. It does have other zeros. How many zeros does it have? 8. Now we know it has 3 zeros here. And then we can try to figure out where the other zeros are. I don't really care right now. This is just an example. The last bit of notation is f has a pole of order n greater than or equal to 0 if f of z is equal to, and I guess at zk, if f of z is an over z minus zk to the n plus an minus 1 over z minus zk to the n minus 1 plus dot 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 plus a0 plus a1 z minus zk plus dot 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 dot. Okay? So basically, it all comes down to the first term that doesn't vanish. And if n is greater than 0, it's a 0. If n is less than 0, it's a pole. So we have lots of different ways we can integrate. So let me keep this theorem on the board first. Let me prove a nice result on accumulation points. And if we get to the central limit theorem this semester, this is actually going to be what we need to make our argument rigorous in some sense. One of the biggest questions I can ask you is, if I give you two functions, are they the same? Right? Given f and g, are they equal? This can be a harder question or more important question than you might first notice. How many of you are familiar with Kepler's 3 laws? Okay, planets travel in elliptical orbits about the sun, where the sun is one of the foci, equal area in equal time, and the period squared is proportional to the semi-major axis cubed. The last one is a little bit more involved. He also had another explanation as to why there were only the number of planets that there were, and it had to do with the number of platonic solids and putting these platonic solids between the orbits of the planets. Okay. That idea has not been immortalized and has not been taught to generations of physicists. Why?
Because it's untrue.
You could use stronger words than untrue, but sure, we'll leave it as it's untrue because this is being recorded, and I don't want this lecture to be rated so high my kids can't watch it. It's false. Okay? When he was trying to understand the orbits of the planets, one of the things that helped is he had the data from Tycho Brahe on Mars. and he was trying to understand the orbit of Mars. And at one point, he writes down the formula to describe the orbit of Mars. He goes, oh, it looks so much like an oval. If only it was an ellipse. If only it was an elliptical orbit. He had actually written down the equation of an ellipse, but not in the format he knew. He didn't recognize he had written down an elliptical orbit. And it wasn't until later that he realized, oh, it is an ellipse. It's just another way of writing the equation down. So you normally write things down for ellipses in terms like x over a squared plus y over b squared equals 1. There's other ways to write down the equation of an ellipse. So if I give you two functions, one of the most natural questions to ask is, are they the same? So how can you tell me if two functions are the same? Or if that's a hard problem, what's another problem you could do?
That they're the same at every point.
So one thing is to just check every possible point. Okay? This is a little time consuming, right? We could, in principle, start checking point after point after point. What if we come to a point where they differ? We're done. Okay. So it's not so bad to show that they differ if we can just find one point where they don't take on the same value. But what if they always take on the same value wherever we check? Maybe we're not checking at enough places. Maybe we're not checking in enough points. So here's the great result. Let's let Fg be holomorphic on open omega, agree on a sequence Zn that accumulates at some point Z star in omega if omega is connected then F equals G on omega. So this is an incredible result. If you have two functions that agree on a sequence of points that accumulate, so for instance, here's omega, and here's my sequence of points zk that's accumulating to something here. And if my two functions agree on this sequence that accumulates, then they must be identical. Now, I'm using the notion of connected. How many of you have not seen connected in real analysis? Okay. So you sometimes talk about pathwise connected, and you sometimes talk about simply connected. Okay. So I basically want to say I have one component. Question?
Is there some specification of like what type, like why, like you obviously can't just choose the constant sequence,
For the zk's?
right?
Well, the zk's are points in omega.
But then
Oh, I see what you're saying. You're good. So in a sequence of distinct points. Yes. Yes, good observation. We assume the zk's are distinct points, otherwise you're correct. We could just be looking at them, and if they agree at one point, they agree everywhere. Yes.
and then that's enough.
That's enough. So as long as it's infinitely many distinct points. Why do you think we have to have the function, the space omega be connected? So the proof should either be much harder if omega is not connected, or there should be a counterexample. So can somebody give me a non-connected set?
The irrational.
Okay. Yeah. We like open sets. I wanted a disconnected open set.
Just take the plane minus the circle.
Okay, so if we take the plane minus the circle, we have the interior region here, which is maybe U1, and the exterior region here, which is U2. Okay. Instead of doing that, I'm going to just, because it's just a little bit easier to draw, let's just draw two disks. So I have two disks. What should I have f and g equal on this disk? Constant function. Let's say f equals g equals 5. And over here, let's take f equals 4 and g equals 5. Is f still holomorphic? Yeah, these are separated. I have to do the limit of z plus h. I'm never going to be mixing points. We will actually see functions that have integer values later in this course. So something like this is not unreasonable. So here, f and g would agree on a sequence that accumulates. They agree everywhere. But the functions are not identically equal. But they're equal in the connected component. And that's really how you should view this, is you want to be looking at what's going on in the connected component. Because these are disconnected, in some sense the knowledge from here does not propagate to the knowledge here. I can define them however I want. What we will often try to do is extend and say, well, look, if I know my function here, is there a way to extend its definition further? And in some sense, we've seen a little bit of that already, and we'll talk more about that later. All right. So let's do a proof of this. Let's let phi of z equal f minus g of z. So now we have a sequence of points where phi is identically 0, and phi is going to be a nice holomorphic function. So what we're really trying to show is that if a function is 0 at infinitely many points, then the function must be identically 0. Is that true in real analysis? If you have a function that's 0 on a sequence that accumulates, then the function must be identically 0. All right. What's the counterexample from real? Yeah. Compare to, let's do x cubed sine of 1 over x, because now the function is differentiable. This function is differentiable, but it's not differentiable infinitely often. And this function is 0 infinitely often as we get closer and closer and closer to the origin. It's actually 0 at the origin, so it's 0 at the point of accumulation. But this function is not identically 0. What do you now immediately know about z cubed sine of 1 over z? It's not holomorphic. Because if z cubed sine of 1 over z was holomorphic, and it accumulates, it would have to be identically 0. It's not identically 0, therefore it's not differentiable. This is the elephant gun proof that this function is not complex differentiable. But if you have an elephant gun, why not use it, right? So this shows you how different of a subject complex is than real. Functions like this exist in real analysis. They do not exist in complex analysis. So we have a function that is 0 on a sequence that accumulates. So 0 on distinct zk converging to z star in omega. Okay. What must be true of phi at z star? Has to be 0. Why? Yeah, phi of z star is 0 by continuity. If you're holomorphic, then you're continuous. So now what we can do is we can Taylor expand our function phi about z star. Wait, do we know we can Taylor expand? Yes, because we are done with the boring part of the semester where we always have to be careful. Now holomorphic is not the same as analytic. Now we can stop worrying about that. We know holomorphic equals analytic. So we can write f of z is, an, let's do it, a k z minus z star to the k plus dot, dot, dot. Right? There's got to be some k that works. We can then rewrite this as a k z minus z star to the k 1 plus c of z. Right? Just pull out the a k z minus z star to the k. A k is not 0. K is greater than or equal to 1. What do we know about c of z star? It's holomorphic. So c is holomorphic, but we know something more. What would c of z star have to be? Has to be 0, right? This is a Taylor series in terms of z minus z star. So we know c of z star equals 0. So that means C has to be small if we're close to Z star. So if we're sufficiently close to Z star, it's at most a half an absolute value. So if Z minus Z star is less than delta, then C of Z will be less than 1/2. Right? Because it's converging to 0.
What allowed you to pull out the 1 plus C?
Well, the next term is going to be a Z minus Z star to the K plus 1, a Z minus Z star to the K plus 2. So I'm just pulling out a Z minus Z star from every term. So this term is then going to have, it's really a function of Z minus Z star. I'm just writing it as C of Z, but it's really, if you want, every time Z occurs, it occurs as a Z minus Z star. And since it's a Taylor series, the next term is going to be a K plus 1, K plus 2, K plus 3. So this has to vanish at Z star. Since it has to vanish at Z star, eventually it has to be less than 1/2. Oh, if this is less than 1/2, this is 0 at Z star. Can this be 0 anywhere else near Z star? Who here has taken abstract algebra and knows about divisors of 0? Where you can have two numbers that aren't 0, but their product can be 0? We don't have that. Right? We don't have that kind of algebra here. The algebra we do in this class is just Taylor series expansions and the algebra from that. This can't be 0 except at Z star. And if Z is sufficiently close to Z star, this is at most half an absolute value. It's not enough to cancel the plus 1. So we know f of Z does not equal 0 except at Z star if Z minus Z star is less than delta. The only point in that region where it can be 0 is at Z star. What's the contradiction? Yes, we are supposed to have a sequence of points that accumulate. We have a sequence of points, Zn, that converge to Z star. We assumed that f was 0 along those points. Oh, I'm calling this f. I think we're now calling this phi. I apologize. Change this to phi. We're looking at the difference. This contradicts the fact that phi was 0 at each of these points. Contradicts phi of Zn equals 0 along Zn going to Z star. And that finishes the proof. So we had said that what is the contradiction? Well, I guess I phrased this not as a contradiction. So I have to remove the word contradiction because I didn't say assume. Oh, no, I do have a contradiction. Where's the contradiction? I did assume something at one point.
AK is 0.
I assumed AK is not 0 and that there's an AK not equal to 0 and there's a K greater than equal to 1. This was the only thing I assumed in the argument. It's very easy to make assumptions and not realize you're doing them. We say, well, look, it's analytic. It has a Taylor series expansion. Let's write it down. AK is not 0 and K is greater than equal to 1. It has a 0 of some order at Z star. There's only one thing that works. What's the only thing that works? There's only one thing that works now. So what must be true? The only thing that works is all the Taylor coefficients are 0. AK equals 0 for all K. So AK equals 0 for all K. So what we've shown is that our function is identically 0 in some neighborhood of Z star. Okay? The rest of the proof is topology. So I'm going to just quickly highlight how we finished the proof. And then we'll go to applications. So we know phi of z equals 0 in a neighborhood of z star. Okay? And now what we can do is we can look at all the points where f is 0. Let U be the subset of omega where phi is 0. And we just showed that this is an open set. Because if you have a point where it's 0, you can have a sequence of points converging to it. Or we can do this from all points. We'll do this from all points with a sequence that accumulates that goes to 0. So U will be, well, phi is 0 for some sequence of points converging to an element of U. So I just take all the points in omega where I have a sequence of points where along the sequence of points my function is 0. And then we show that that point that it converges to is 0. And then it's also got to be 0 in a small neighborhood of that. Well, if it's 0 in a neighborhood of that, once we know it's 0 at z star, there's some neighborhood around z star where it's 0. Any point in here now, we have a sequence of points that converges to it where it's 0. So this entire region would satisfy this definition. So U is an open set. U is also a closed set because by continuity, if you're in this set and you look at a sequence of points in this set, well, they're always equal to 0. They'll converge to something and by continuity. So here's the sketch. 1, U is open. 2, U is closed by continuity. So 3, we can basically write omega as U union omega minus U. And you cannot write an open set as a union of disjoint open sets.
You can't write an open set as a union of disjoint open sets.
If it's connected.
Oh.
Of open sets if connected. At some point in the proof, we should use the fact that a set is connected, given that there's a contradiction or a counterexample when it's not. And essentially, we can only prove things about connected components. And so here, this is where a little bit of topology is going on. There's some stuff in the book if you want to do this. If you like topology, make this part rigorous. The basic idea is the following, and I just want to recap the proof because it's such a nice proof. You have two functions. Might as well look at their difference. Makes the algebra a little bit simpler. So we have two functions, we look at their difference, and we're 0 along a sequence of points that accumulates. By continuity, the function has to be 0 at that point. Because holomorphic is the analytic, it has a Taylor series expansion about that point. We can then show by pulling out the leading term that whatever's left over is going to be really small because it's a convergent series. And so the only place it can be 0 in a small neighborhood, if any of the Taylor coefficients aren't 0, is at z star. But since we know it accumulates, that's a contradiction, so all the Taylor coefficients have to be 0. So we now know that our function has a Taylor series that's identically 0 in some neighborhood. And so that doesn't prove that it's 0 everywhere in omega, it just proves it's 0 in a little region. And then you need to show that just expands outward. Well, once I know it's here, then I can expand anywhere on the boundary, then I can draw an open set, and it's going to be, then I can keep just pushing these open sets out. And that's the whole argument. Imagine there's some point it doesn't push out to. What would that mean? What can you do? And that's where you just need to use just a little bit of topology to finish things up. So this is an extremely useful result. If you can show that you have agreement along a sequence that converges, then you must be identically 0. Okay, any questions about this? So this is something we're going to put in the bank for later in the semester when we get to the central limit theorem.
Sorry, the closed by continuity is just because all the sequences of 0 are containing their
Because our function is continuous, if it's 0 along a sequence, then wherever the sequence converges to, it's got to be 0 at that point by continuity. And so, okay. So let's do an example with Cauchy's formula. So we did 1 over 1 plus x squared, I think in class on Friday. I scanned some notes of doing 1 over 1 plus x to the 4th. Let's do a harder one. Let's do 1 over 1 plus x cubed. And ideally, we would love to do this from minus infinity to infinity, but that would have an explosion on the line of integration. We don't want an explosion on the line of integration. So we have to find a better contour. One thing is we can still do like this minus infinity to infinity stuff. It kind of maybe do some kind of swivel or pivoting around the point x equals -1, where bad things are happening. Or we can try to look at things a little bit differently. So here's the example. 0 to infinity of 1 over 1 plus x cubed dx. And so we actually, if you know probability, if you have a non-negative function that integrates to, say, 5, if you divide by 5, it integrates to 1. It's now a density. We need to figure out what this integrates to. Sometimes in probability, they put an absolute value along x, so you could have a distribution that takes both positive and negatives. If we do that, we would just double whatever this is or halve it. So it's enough to be able to figure out how to integrate from 0 to infinity. So where are the danger points? The danger points are when the denominator blows up. As long as x goes from 0 to infinity, we have no danger points along that. And the function has enough decay that the integral makes sense. So this is at least a question that we can ask. Okay? So we have even and odd functions, right? Why is an even function nice? What does it mean for function f to be even? Okay, so f of negative x equals f of x. Is this function even? No. If you replace x with negative x, you have something completely different. But is there a generalization? Instead of putting a -1, what could I put in and have the same value come out? F of something times x equals f of x. What should I put in here? Oh, okay, good. Good. This is what I'm trying to get. I'm trying to get you to see why this is a natural thing to do. I don't want to just jump down and write the answer. I did that for the older complex analysis students. I didn't like them as much as I like you guys.
You could put a 1.
I could put a 1. I think I can also throw chalk at you. I think as a tenured professor, you can't lose your job for throwing chalk at people. But I will double check that. You could put in a 1. Could I put in something other than a 1?
Do e to the I pi.
Yeah, I could do e to the I pi over 3. Or I could do e to the 2 pi I over 3. Or is 2 pi I what I want? Yes, 2 pi I over 3 would work, right? And I could also, wait. No, wait a minute. No, if I put in e to the pi over 3, that would give me a -1. I want, I think, 2 I pi over 3. Right? Right. So if I do e to the 2 pi I over 3, if I cube this, e to the 2 pi I over 3 cubed is just e to the 2 pi I, which is 1. I could also do e to the 4 I pi over 3, and I could do e to the 6 pi I over 3. And the 6 I pi over 3 is just the one that was suggested. This is the non-trivial one. So this is not a function that's even, it's not a function that's odd, but it has a really nice symmetry with respect to e to the 2 pi over 3. So if I were to draw a picture, e to the 2 pi I over 3 would be something like that. So what I'm hoping this motivates is choosing this is your contour. R, and this point over here would be RE to the 2 pi I over 3. This point over here would be, I think, I times R. Because along this line, I'm going to essentially be getting back the function I had before. So the whole point is to try to understand how we choose the contour. There's a little bit of art in the subject. So you have two things you have to do. You have to choose the function, and you have to choose the contour. Usually the function is pretty clear. It's essentially do a search and replace. Every time you see x, shove in a z. You might have seen something similar to this in the integral test in Calc 3. Well, you need to find a function to compare your sequence to. Normally you see n, and you replace all the n's with x's. And that gives you your function for your integral test. Fortunately, that level of sophistication continues as we go into complex analysis, and replacing x with z most of the time does a good job. Sometimes you might want to just look at like the real part, because rather than doing sine and writing sine as a difference of two exponentials, it's better to just say it's the imaginary part, and you're just putting in something that integrates to 0. All right, so now we have, let's take f of z to be 1 over 1 plus z cubed. We're going to have 3 pieces for the contour. On this piece, dz equals dx. And that part we know how to handle. That's going to be the integral we want. On this piece, on this circular arc, is there going to be a contribution from that circular arc in the limit? So on this circular arc, approximately how large is the function? 1 over r cubed. Worst case scenario, it's 1 over r cubed minus 1 in absolute value. So along here, f of z is less than or equal to 1 over r cubed minus 1. Could we figure out exactly what the perimeter of this is? Yes. Do we care? No. It's probably 1/3 of 2 pi. But I'll just say it's at most 2 pi. Because that way I'm safe and I don't have to risk doing algebra. Even the good type of algebra. Or the better type of algebra. I'll say better type of algebra. Right? The perimeter of this is at most 2 pi r. The maximum value is 1 over r cubed minus 1. So if I look at the product, I'm going to get something that looks like some constant over r squared. So as r goes to infinity, the contribution from this piece is negligible. If I had, instead of x cubed, if I just had x, then I'd be in trouble. Because then the denominator would be r minus 1. And when I multiply by 2 pi r, or 2/3 2 pi r, I would have something of size 1, and that would contribute. All I need is something greater than 1 over there. So are we all comfortable that there will be no contribution from this arc? Now let's look at what's going on here. So along here, this will be the equation z equals e to the 2 pi I over 3 if you want times x. So dz would be e to the 2 pi I over 3 dx. Okay? So I can figure out how I want to parameterize all these things. I'm using the variable x because I'm going to have an x integral here. It turns out this integral is going to align with this and be like a multiple. So in calculus, you might have seen something called like the bring it over method, where you have an integral and you maybe integrate by parts twice, and you get back the integral you started with, but with a multiple of like 1/4 in front of it. And so you basically get integral equals something known plus 1/4 of your integral. So then you get 3/4 of your integral equals something that's known. So your integral equals 4/3 of what's known. And so you never find the integral directly, but you get it on both sides with unequal weights. So this is called the bring it over method. We're going to do the same thing here right now. Okay, so now the only problem left is we have to figure out, where does this function blow up? So where are the poles of f of z. So what do we need to find the pole? What must be 0?
1 plus x cubed.
So 1 plus z cubed, 1 plus x cubed. So we want 1 plus z cubed equals 0. So we want z cubed equals -1. So z is an element. So the first thing that cubes to -1, -1 is e to the I pi. So we want e to the I pi over 3. And then what do we add to it? We can add 2 I pi over 3. And we can get e to the I pi. Good. -1 cubed is -1. And then the last one would be e to the 3 to the 5 I pi over 3. So those are the 3 places where it blows up. If you're not comfortable with this, we could, of course, factor this as z minus 1 times z squared plus z plus 1, and then you could use the quadratic formula. If you can see the factorization, by all means, avoid the quadratic formula. So of these 3 points, which is the only one that's inside our region? Yeah, the first one, e to the I pi over 3. So here is e to the I pi over 3. All right. We've been keeping Cauchy's theorem up on the board the whole day. Now we can finally use it and then erase it and get more board space. Right? It says that the integral is equal to the sum of the residues at the poles. There's only one pole. So what we get is 1 over 2 pi I, the integral of a closed curve of dz over 1 plus z cubed is equal to the residue of our function f at the point e to the I pi over 3. So now all we have to do is figure out what the integral is along the third part, and then we have to just figure out what is the residue at e to the I pi over 3. All right. We've got about 6 minutes left. Hopefully that will be enough time. If not, I'll just start using words like obvious, clearly, one can readily see that, and we'll finish. Okay? Which do you want to do first, residue or the integral?
Residue.
Okay, first loud voice wins. So we have residue. So we have 1 over z cubed plus 1. And we want to find the residue of this at e to the I pi over 3. So there's a couple of ways to do this. One is to start playing games. And we can try to expand things out, but we also know this is 1 over z minus z1, z minus z2, z minus z3, where these are our 3 roots. You know, z1 is e to the I pi over 3, etc. So let's look at what we have. We have 1 over z minus z1, and then over here we have 1 over z minus z2, z minus z3. Is this function well behaved at z1? Yeah, it's holomorphic. So this has a Taylor series expansion. This is equal to some function, call it, phi at z1 plus phi prime of z1, z minus z1 plus dot dot dot. Right? It has a Taylor series expansion. All I care about is this piece. I just care about the residue, the -1 term. This term would give me a constant. The z minus z1's cancel. So all I have to do is, when I want to find the Taylor series of this, I only need to find the constant term of this Taylor series, and that will give me the residue. If I had a z minus z1 squared, then I would have to find the linear term. How do I find the constant term? Just plug in z1. So this is equal to 1 over z minus z1. Then the constant term is 1 over z1 minus z2, z1 minus z3, plus something that's nice. That's the residue. All right, so the residue isn't that bad. So we'll come back over here. I'll get some of my steps in. And so we get 1 over e to the I pi over 3 minus e to the I pi, and then e to the I pi over 3 minus e to the 5 I pi over 3. Okay? So we've now calculated the residue. Okay. I'm going to keep the picture up. And now all we have to do is we have to figure out the integral over here. We have 3 pieces. We already know one of them. Let's get the other 2. Can I erase this now? Everybody comfortable with the residue? So this is a great lesson in life. For many things, only answer what is needed. The rest is not needed for this problem. It will not help you at all. There's no need to spend more time on that. So now, integration. So we can call this gamma 1, gamma 2, gamma 3. As r goes to infinity, the integral over gamma 2 goes to 0. We showed that. The integral over gamma 1, 1 over 2 pi I, goes to 1 over 2 pi I, integral x goes from 0 to infinity of dx over 1 plus x cubed. The other one, 1 over 2 pi I, integral over gamma 3, f of z dz. This is 1 over 2 pi I, integral, what's the initial value of x? R. So you go from r to 0. Now here dz is e to the 2 pi I over 3 dz, dx over 1 plus x cubed. And now we're using the fact that if we take z equals e to the 2 pi I over 3x and we cube that, we just get x cubed. Okay, well, if we flip the order, that just introduces a minus sign. So as r goes to infinity, we get 1 over 2 pi I with a minus sign, integral from 0 to r, e to the 2 pi I over 3, 1 plus x cubed dx. Does this depend on x? And then as I goes to infinity, that becomes infinity. So what we get is 1 over 2 pi I integral over gamma f of z dz is just 1 over 2 pi I, and then we'll have 1 minus e to the 2 pi I over 3 times our integral 0 to infinity of 1 over 1 plus x cubed dx. Okay? And again, this is the bring it over method. We essentially have the integral we want twice. And because this is a constant factor and it's not equal to 1, this is non-trivial. So therefore, the integral from 0 to infinity of dx over 1 plus x cubed is 2 pi I 1 over, we've got z1 minus z2, I need to save chalk time, z1 minus z3, and now this has to go down below, 1 minus e to the 2 pi I over 3. And there's the answer. If this answer means something to you, you are a better mathematician than I am, right? Does this look like anything meaningful? No. Okay, what do we do for something like this? We have to plug in what are z1, z2, z3, and expand everything out. This is where something like Mathematica is wonderful, right? So let's see. What was z1? Z1 was exponential of I pi over 3. Z2 was exponential of I pi. Z3 was exponential of 5 pi I over 3. All right, so we have z1 minus z2, z1 minus z3, and then the last one was 1 minus exponential of 2 pi I over 3. Okay. And when you plug this into Mathematica, you end up getting a nasty thing which it doesn't do anything to. But if you put the word simplify in front of it, oh, Shaza. Oh, wait, we have to then multiply by 2 pi I, right? And 2 pi I is in the top, right?
Yeah.
So when we put that in front, 2 pi I, all right, so this must be a small algebra mistake because I'm not getting a real number. So this is always unfortunate when this happens.
Is there a minus sign missed?
I really hope so. I really hope so. Where's the minus sign missed?
The, well, sorry.
Yep, no.
Right there. It seems like there's...
Well, no, but that... Oh! No, that minus sign was from flipping the order.
Yeah.
Right? So I thought we included that.
But where did it show up in the next expression?
Because when we were combining them, when we had this integral is going from x equals r to 0. So we have to put in an extra minus sign. And that's where that minus sign came from. Going from this line to this line.
Yeah, but I mean, where did it go in the next one?
Well, then it's just when we added that to this one had a 1 over here, so we had a 1 minus e to the 2 pi I over 3.
No, negative. Pi over 3 over pi I.
I will put that plus sign in there and see if that works. I still have an I there. So there's a small algebra mistake that I will find. So unfortunately, the algebra did not work out at the end. The principle is correct. All right. So we will then check and try to find out where's the minus sign. If somebody finds the error before I do, that's worth an extra credit point because it means I don't have to find it.